Earlier this week we talked about the bond angle in water, how a completely equal tetrahedral geometry would put all of the bonds 109.5 degrees apart. But experimentally in water we see that the two hydrogens are only 104.5 degrees apart, because of the extra pressure put on them by the lone pairs. Valence shell electron pair repulsion theory makes good intuitive sense. Negative charges are going to repel each other. But how do we square those shapes with what we already know about the electronic orbitals and the electronic structure of the oxygen atom? The valence shell of the oxygen atom contains 6 electrons in 4 orbitals, and each hydrogen atom contributes 1 electron in 1 orbital, completing the octet. Let's try to fill those orbitals as they are. First we'll put 2 electrons in the 2s orbital, and the remaining 4 in the 2p orbitals. We can complete the octet by including the 2 single electrons provided by the 2 hydrogen atoms. Now if we try to draw the oxygen molecule based on its electronic structure, we get one set of lone pairs, 2 electrons in the 2s orbital that are just sort of floating around, and the 2 hydrogens 90 degrees apart. Even though the quantum mechanical solutions for the atomic orbitals tells us that the p orbitals must be 90 degrees apart, that's not where we see the bonds forming experimentally. And this tells us that our theory must be incomplete. The same mathematics we used to determine the orbital shapes in the first place also tells us that those same orbitals, the s and p and d and f orbitals, can be combined into hybrid orbitals that are just as legitimate and might actually reduce the overall energy of the new molecule. For instance, instead of keeping our single 2s orbital and our 3 2p orbitals separate, we can combine them into 4 orbitals, each equal in shape and size, in distance from the nucleus, and in angle from each other. How does it look when we combine some s and p character? We get something that's sort of spherical and still sort of lobed. Each of these new hybrid orbitals are on the same energy level, between the 2s and the 2p. And when all of the electrons in the molecule are considered, this new arrangement creates the lowest overall energy, and, as an added bonus, it actually agrees with physical reality. Now when we draw the water molecule, we have 2 sets of lone pairs in 2 arms of a tetrahedral arrangement, and 2 hydrogen atoms on the other 2 arms. Any combination of orbitals is allowed, so if the molecule only needs to hybridize the s and 2p orbitals, then we get an atom with 1 p orbital and 3 sp2 hybridized orbitals. Or we can hybridize 1 s and 1 p orbital, leaving 2 p orbitals and 2 sp orbitals. For third row atoms, we can also start adding the d orbitals. This explains how phosphorus and sulfur can take more than an octet of bonded atoms. An atom in an octahedral geometry needs at least 6 regions of electron density. That means combining 6 different atomic orbitals, 1s, 3p, and 2d orbitals, into 6 equivalent hybridized orbitals. Next time we'll discuss what happens when we try to connect hybridized orbitals together to form a molecule.